Hello students, welcome to the course Circuit Theory and Network. Today we are going to discuss the Thevenin's theorem for AC network. In the last video we have seen what are the different types of steps for Thevenin's theorem and if there are any DC networks are there and how we can apply that Thevenin's theorem. And today we will see if any AC networks are there, how we can apply that Thevenin's theorem. Okay. So, for the Thevenin's theorem, as the statement was for the DC network theorem, the statement will be same. The same things will be there. Just in place of Thevenin resistance, there will be the Thevenin impedance. It means in the place of RTH, we will write ZTH, because we know in case of DC circuit, as the resistances are there, and similarly in case of AC circuit, with the resistance there is one another part that is called the reactance, and altogether this resistance and reactance, that is called the impedance. So we will write over here ZTH. So the statement is as like the previous one. It means for any linear active bilateral AC network, the load across its terminal AB can be replaced by a simple equivalent circuit having single AC source voltage VTH in series with a single impedance, that is called ZTH, where VTH is known as the Thevenin voltage or the open circuit voltage, whatever we have considered for DC network theorem, the same, and the ZTH, that is called the Thevenin equivalent impedance, and which we have to view it from the load side obviously, or the terminal where we are going to apply this Thevenin's theorem. It means from where we are going to find out the current or where we have considered the load resistance, right? So now the steps is as simple as that, just like the previous one. It means first you have to identify which one is your load resistance or which one is your load impedance. First find out that load impedance, as we are considering about AC circuit, so always we will consider impedance instead of resistance. So first you have to identify the load impedance, then you have to remove that load impedance, and you have to find the voltage at that open circuit terminal, and that voltage is called as the Thevenin voltage or the open circuit voltage. And the next is you have to replace all the sources by their internal equivalent resistance. If there are voltage source, if there are current source, just like the previous one, just like their equivalent voltage source, you have to replace the sources and you have to look from the load side. It means where your load impedances are there, and you have to look for the overall impedance of the circuit, and that impedance will be called as a Thevenin impedance. And after finding this Thevenin voltage and this Thevenin impedance, just we have to connect this Thevenin voltage and Thevenin impedance in series with the load impedance, and then you have to put the formula just like the previous one. So these are the overall steps, and we have to follow these steps to solve any types of problem. So simply suppose these are the steps. So from that circuit we have find out Thevenin voltage and Thevenin impedance, and there are the Thevenin there are the load impedance that are connected in series with each other. And as there is a series circuit, simply you have to find out this IL or this load current, and simply we can say that amount of this IL, it will be nothing but a IL is equals to VTH divided by ZTH plus ZL obviously. And just like the previous one, we can say that if we write I of L, load current, is equals to it will be V of TH divided by ZTH plus ZL, okay. So now we are moving to the next for a problem how we can solve a circuit. Okay. So here one circuit, we have considered one circuit, and we are asking you to find out the Thevenin equivalent circuit of the network viewed from the terminal A and B. So A and B terminal is over here, it's given, and we have to find out the Thevenin equivalent impedance or the Thevenin equivalent circuit. So Thevenin equivalent circuit means you have to find out the Thevenin voltage as well as you have to find out the Thevenin impedance. It means ZTH. So as per our first step, so as we have to find out the parameter across the terminal A and B, and so this 2 ohm resistance over here, so this will be considered as a load resistance. So as per the step 1, we have to remove this load. So if we remove this 2 ohm load, so the circuit looks like this, and obviously the sources will be over there if we are going to find out VTH. And if at first if we are going to find out the RTH or ZTH, then simply replace all the sources. Here first we have find out the RTH or ZTH. So for the finding this ZTH, first we have replaced all this load resistance, and as there is a source, this is a voltage source, obviously it's AC source and AC voltage source, and we know the voltage source having the internal resistance or internal impedance that is also negligible. So we can replace these sources and we can short the terminal, right? So as we have short the terminal, and this is our load impedance or load resistance was there, and we have replaced it or we have removed it. So we will look from this side and to find out the overall impedance of the circuit, to find out our ZTH. So we know this branch having this is an inductance, and inductance are connected over here, and inductor is connected over here, and the value is given in terms of 8 ohm. 8 ohm means here the impedance value is given, the impedance for the branch that is given over here, and here the value is given as 6 ohm. 6 ohm. So obviously as the values is 6 ohm and 6 ohm for this capacitor and 8 ohm for this inductor, and we know for any inductor or any path having any resistance in series with any inductance or in series with any capacitance, we know that Z is equals to, we can write Z is equals to obviously R, capital R, plus JXL minus JXC. So this is our general formula that we have seen in already in our basic electrical classes, JXL minus of JXC. So if any branch consists with a resistance, inductor and capacitor in series with each other. So if we consider this path, this path having only one inductors are there, so obviously there the values of only XL, JXL, it means these values are given to us, these values is given to us. So R value is 0, JXC values is 0. So for this path or the path or the impedance of this path, that is written as a Z1. So Z1 is nothing but Z1 is nothing, we can write Z1 is written as a, this R is equals to 0, and obviously JXC, XC value is there is no more XC in this particular path, so there is no C, so this XC value is 0, so this term is 0, and JXL, and XL value, this 8 ohms value means this value is given as a reactance values of this inductor of this inductor. So reactance value means XL, XL means we know omega L, and this value XL value is given. So this 8 ohm, that is the values of XL, and this 6 ohm, that is the values of XC, values are given. So as per this formula, our Z1 will be 0 plus J into 8 minus J into 0. So obviously we can find that Z1 is equals to J of 8 ohm. And similarly your Z2, it means for this branch, the impedance means by using that formula, this path having no more resistance, this path having no more inductance, and this path having only the capacitance, having the capacitive reactance values of 6 ohm. Capacitive reactance value, it means XC values have the 6 ohm. So similarly we can find that our Z2 having a values of R is equals to 0, XL values of 0, and minus of J into XC value is 6, so minus J6 ohm. So this is our the values of Z1, and this is the values of Z2. Now if we look from this load side, we can simply see that the overall impedance across the terminal A and B, that will be nothing but a Z1 in parallel with Z2, Z1 in parallel with Z2. Z2. So the overall impedance across this terminal, it means the ZTH. So ZTH obviously we can write, that is ZTH, that is will be nothing but this Z1, whatever the values of Z1 in parallel with the values of Z2. Now put the values of Z1 and Z2 and you will get the value. And obviously you know how we can for this AC circuit there is a change of coordinate from polar to rectangular and from rectangular to polar, etc., and it will be required, and I am coming to that part later. And so I am going to the next slide, and for the next so as per the formula of ZTA, Z1 into Z2 divided by Z1 plus Z2, at Z1 and Z2 they are parallel to each other. Now here the values is 8 angle 90 and 6 angle minus 90. Now here is a little bit, I think you are little bit confused that how the values are comes. Actually the values of Z1 is previously you have seen that values of Z1 was there in 8 J8 Z1, that was written as a J8 plus of J8, and the values of J2 that is written in like this, minus of J6, minus of J6 ohm, obviously minus of J6 ohm. Now this J8 and J6 that it was your in rectangular coordinate. Now for this these types of calculation it will be very easier to calculate if we can convert this any component from rectangular coordinate to the polar coordinate, then your multiplication or your division operation, that will be very easier. That's why we have changed the values of this Z1 and Z2 from rectangular coordinate to polar coordinate. It means the rectangular coordinate where we can represent any variable like a plus ib, like a plus ib or a plus jb. If we represent for the rectangular coordinate, for the rectangular coordinate, and similarly for the polar coordinate we can represent the value as a r theta. It means r and angle of theta. This is our rectangular, this is our polar coordinate, polar coordinate. And if there are any confusion regarding this rectangular and polar coordinate conversion, then obviously we can make another video where we will clearly see discuss that how we can convert this rectangular to polar conversion. Okay, so by conversing you can also convert this rectangular coordinate to polar coordinate by your calculator also, no problem at all. And if it's not clear to you, then also you can go for the video where we have discussed about the coordinate conversion, like polar to rectangular coordinate and rectangular to polar coordinate. And by using that formula we are getting that these types of value, that 8 angle 90 and Z2 has a values of 6 angle of minus 90, and both the values of Z1 and Z2 after going to add them, where the polar coordinate value is 2 angle 90. So now when all these values are in polar, and for this multiplication and division they are very much easier for this polar coordinate. It means if the values are like this, suppose if we can write as like this, suppose r1 and theta 1, r1 and theta 1, r1 and theta 1, and it's going to multiplied with another polar coordinate like r2 multiplied with theta 2. Simply the overall value comes like this, that r1, the values of r1 that is multiplied with the values of r2, it means the value comes r1 into r2, and whatever the angle values are there, this angle value is just simply added at the time of multiplication. So what is the angle value? The first one, the angle value is theta 1, and the next time the value was theta 2. So simply add this value theta 1 and plus of theta 2, that is your value. So by that rules, if we there are 8 and 6 and angle is plus 90 and minus 90, and obviously the multiplication 8 into 6, that is 48, and angle that is 90 plus of minus 90, it means angle is 0, divided by 2 angle 90. And similarly at the time of division it's also very easy for the polar coordinate. It means if the same things happen like this, suppose I'm going to erase this portion, otherwise it will be very difficult to understand. So suppose this R1 and R2s are there and we are going to divide it. Suppose R1 theta 1 and divided by R2 into theta 2. So the overall value comes like this, R1 divided by R2, and whatever the angle will be theta 1 minus of theta 2. So by using that formula here, if we divide it, so here the value is 24, and as the time of division the angle value will be subtracted, so it comes the minus 90. So this value, this is your the values of ZTH or the Thevenin impedance value. This is your Thevenin impedance value, right? Now we have to find out the Thevenin equivalent voltage. Thevenin equivalent voltage. Now for the Thevenin equivalent voltage means where the resistance was connected, or the load resistance or the load impedance was connected, and that point is open, and we have to find out the voltage over here. For this voltage we are going to find out the voltage, we are going to apply the KVL in that particular closed path, and obviously this voltage in the across this A and B terminal, this is nothing but a voltage across this branch, right? So first of all, if we are if we apply the KVL in this path, it will be suppose there is a current I. If we consider there is a current I over here, it means here is this branch current I is over here. So obviously this I amount of current should be over here, and as this path is open, so no more current over here. So we can write I into J8. If we can convert this J8 to polar rectangular to polar, that will be this value, or if we go for the simply rectangular coordinate, then also no problem. So I into J8, so we can write I for the equation I into J8, capital I into J8, then this value will be plus, so plus of I into minus J6, so plus I into minus J6, so that will be plus of minus I into J6, and obviously as this side is positive, so this side is negative, it means it's not positive, so if this side is dots are there, it means for any moment this side is positive, so this side will be negative. So minus our angle is tan angle 0. This is the values of the voltage source, minus tan angle 0, that will be is equals to 0 for this closed path. So simply from over here, if we can write, so if we take a common of I, so if we take a common of I, so it will be J of 8, and there will be a plus and minus, it will be obviously minus J6, and minus of J6, and will be is equals to, that will be in right side, that will be obviously your tan angle 0, J8 minus J6. J8 minus J6 will be is equals to tan angle 0, and the same equation is given over here, and if we rearrange the equation, and the equation looks like this, the equation looks like this, and from here we can find out the values of current. And for the values of current, again there is a requirement of the conversion from polar to rectangular or rectangular to polar. If required, then we will solve it, and then we are getting the values of capital I, that is 5 angle 90 ampere. So this is the amount of current which is flowing through this path. Now what is the voltage across this path? Now voltage across this path means whatever the current flowing through this path multiplying with the impedance of that path. So this VTH is nothing but a voltage across this terminal. Suppose if we consider this terminal is a X and this point is Y, if we consider, so your VTH is nothing but we can write that is of V of XY, V of XY. And what is the values of V of XY? The current multiplying with the impedance value. Current is I, amount of current is I, and impedance, that we know that this branch we have considered the Z2 impedance, so I into Z2 impedance having a values of minus J6, and I value that we are getting 5 angle 90. Obviously there is an 5 angle of 90, there is an angle 90 values are there, 5 angle of 90, here is the value 5 angle 90. So all these values are multiplied over here, and by solving that we can find out that this VTH is 30 angle minus of 180. So this is the values of VTH or the Thevenin voltage. So already we have find out the Thevenin impedance ZTH over here, we have find out VTH over here. right? So now what will be our equivalent circuit? Our equivalent circuit must have VTH in series with ZTH and in series with ZL, right? So go for the circuit design. So for the circuit in series VTH in series with ZTH, there will be in series with RL or the load resistance, whatever are there, load resistance, whatever are there, load resistance or load impedance, whatever we can say. If there are load resistance, we will write load resistance RL. If there are any impedances are there, suppose generally impedance will look like a it looks like a box, and there is written RL or ZL, that is load impedance that we have removed the first time. So these are the value of this Thevenin voltage, and this was our values of this Thevenin impedance ZTH, and this is our ZL. So now what is the current flowing through here? So if this current is amount, if we consider this current is I, or if we consider this current is IL, so now again we can apply KVL over here. We can write IL into Z of TH, IL into ZTH, IL into ZTH, plus if we consider ZL over here, so ZL into IL, ZL into IL. Again, if we consider there is a polarity of this side, so this will be your minus of VTH, minus of VTH, that will be is equals to 0. So simply we can write IL, if we take a common, IL into ZL plus ZTH is equals to VTH will be over here, and in the next step we can write IL is equals to VTH divided by ZL plus Z of TH. So like that you can apply this Thevenin's theorem for AC network also.